Remember the big three. We are looking at these three right here. Position equation, velocity equation, and the v squared, also known as the no time equation. So read the question, and then we think about like what's given to us, and then what's it asking. So in this case, we're starting from rest. So we know v naught's equal to 0. We have an acceleration, and we have a time. So if you think about, okay, how far did it travel? Probably makes the most sense to look at this one. The position equation involves initial velocity, acceleration, and time. So I just wrote down in the abstract the position equation. I highly suggest writing in the abstract, meaning letters only, the equation you want to use, and then I went ahead and made some substitutions. I want to know where I'm located, in this case, how far I traveled. I had no starting position and I had no initial velocity, so both of those terms drop out. So the position equation turns into just a 1/2 AT squared. Type it in and get an answer, right? So 50 meters. What was my top speed? Well, I am accelerating the entire time, and I started at rest, so I'm using the velocity equation, right? Second equation, standard. V naught's equal to 0, and I simply just take the acceleration of 4, and I multiply by 5, right? 4 meters per second squared, 4 or 5 seconds, is increasing my velocity by 4 meters per second every second for 5 seconds. I thus increased my velocity by 20, and since I started at 0, my top speed must be 20. All right, a driver car is traveling 20 meters per second. He sees an accident and he needs to stop. Okay, and reminder, we're stopping. So our final velocity is 0. Stopping, 0. I have an initial velocity of 20 and I have a distance. Ding, 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 ding. This is reminding us, oh, this is probably a really nice one to use the no time equation. We don't care about time. Initial velocity is 20. I don't know why I did this. I normally would not. I normally would just put a minus sign there because I'm clearly stopping. And I put a minus sign there, and then 2a, and then 50 for x. And then I would get an acceleration of 4, and clearly the acceleration is negative because I am moving to the right and slowing down. But either way, I do need that as an answer. And again, but I agree, most of the time on the board, since I know I'm slowing down, I am going to put a minus sign right here. And then my solution will be a positive, but then I'll write it as a equals -4 meters per second squared. Either way works. Now I'm interested in the time it will take. Well, you can do two things. You can go to the position equation and solve for time, or you can just use the velocity equation. I do know I started at 20. I'm slowing down at 4 meters per second every second. It's going to take me 5 seconds to stop. Right? That wasn't too bad. And really, we could have done part B and then done A, but we just did them in the order it was asked, which is not always the case. All right, an object is moving at 30 and starts to accelerate at a -2 meters per second squared, and now I want to stop. Again, almost all of these can be done in our head because, in reality, equations like this make sense to us. Clearly, the velocity is the original velocity plus or minus what you did and for how long. And so if we're changing our velocity by -2 meters per second every second and we start at 30 meters per second, well, it's going to take us 15 seconds. So I wrote down the equation I want to use in the abstract. I then filled in the numbers, and then I solved. And again, I would argue we could have done that one in our head. Now, how far am I going to travel in that instance? Well, we can do two ways. Don't we know we stopped in 15 seconds? So we can use the position equation. So here's the position equation, right? I'm not sure you can see that t squared at the end, but it's there. And I plugged in just 15 seconds. So I did 0 plus 30 times 15 minus 1/2, 215 squared, and I get 225. Or I can use the v squared equation. Started at 30, went to 0, slowing down at a rate of 2. How long will it take? Either way, v squared or the position equation. A train starts with some unknown velocity. We know it travels 2,000 meters in 8 seconds, and it was accelerating that the whole time. Probably a variety of things, but looks like I did. I think this is probably the easiest. I used the position equation, started from the origin. I went 2,000 meters is the total distance. That's where I ended up. I know my time was 8 seconds, I don't know how fast I started at the beginning, but I know I was accelerating the entire time at 4, so I know everything here but V naught, and you solve for V naught and you get 234. If I wanted to actually find the final velocity, well, I do know I was accelerating at 4 for 8 seconds, so I increased this by 32 meters per second. Again, 4 meters per second squared, 8 seconds is an increase of 32. 32 added to 234 is 266. A car increased its speed from 10 to 22 in 4 seconds. It's kind of like the definition of acceleration. Acceleration is how much, I shouldn't say how much, it's the rate at which you change your velocity. And look, we changed our velocity by 12 in 4 seconds. That's an acceleration of 3 meters per second every second. Could have done that in your head, or you can look at the equation. Went from 10 to 22 for 4 seconds. What rate was required to do that? Well, an increase of 3 meters per second every second would be required. How far did it go? Well, in this case, I used the position equation. Started at rest, so that just is 0. I knocked that out. And I was going, V naught was 10 for 4 seconds, accelerating at 3 for, a 1/2 t squared. You end up showing that you traveled 64 meters to accomplish this task. All right, a runner jogs out at 10 meters per second for 100 meters and then sprints back at 10 meters per second. And the runner returns to its original spot. Part B says find the average speed of the workout. Okay, so let's find out. To find information about speed, well, definition of speed is distance over time. So let's go to always the definition if you get confused, right? We need to know the distance traveled and time. When we know the distance traveled, it's 100 meters out and 100 meters back. There's your 200. Now we got to figure out the time. Okay, so let's look at the jogging out part. Jogging out at 4 meters per second for 100 meters is going to take you 25 seconds. Sprinting back at 10 meters per second, traveling 100 meters, is going to give you 10 seconds. Thus, the entire workout was 35 seconds. So let's go back to the question. Find the average speed of the workout. The average speed of the workout is the total distance, 200, divided by the total time of 35 seconds. You can barely see this on the sheet, but I do believe it says 5.71 meters per second. Again, it is not it is not 7. 7 is the average of 4 and 10, but think about it. You're jogging at 4 meters per second, way longer than you're running at 10. And so this is going to count more, so the average should be shifted towards 4. All right, should the average speed be 7? Again, you jogged for a longer amount of time. The average speed will be closer to your jog speed. You did it for 25 seconds. You only sprinted for 10 seconds. Now, if I asked you for your average velocity, it's kind of like a trick, you got to say 0. And the reason is, go to the definition. Average velocity is delta x over delta t. Well, considering you got back to where you started, you actually had no displacement. So your average, you didn't have any velocity either. All the velocity to the right counteracted with a velocity to the left and led to an average of 0. Remember, velocity is a vector. Speed is a scalar. This last one, we have a 3-phase piece. We got a bike rider traveling at 8 for 4 seconds. Then he accelerates for another 3 seconds, and then he slows down. And so you got to think about on these 3 pieces. So let's think about the first part. Started at the origin, so make that 0. Started at, just traveling at 8 meters per second for 4 seconds. The acceleration is 0, so we don't need that term either. So we're just traveling at 8 meters per second for 4 seconds. So during that first phase, we simply went 32 meters. All right, phase 2. Now we are what? Well, we are currently traveling 8 meters per second, because that's what we were, and we're 32 meters to the right. And now we do this. 32 meters to the right, when that part starts, still having a V naught, an initial velocity of 8, but now we're accelerating for 3 seconds. So I put an acceleration of 2, a time of 3, and I get a new position. This is where I ended up after that second phase. Okay? Now what's going to happen? Now let's look at the third part. Okay, third part, kind of over here. Well, we are going to, what we're going to do? Oh, we're going to slow down to a complete stop. So when we stop, we know we have a velocity of 0. So I want to look at the velocity. We want to stop, started at 14. Oh, we didn't know that yet. Sorry, need to come back over here. So let's figure out, during this third phase, we got to figure out how fast we got to. So during the second phase. So during this second phase, we were traveling at 8. You can't see this, 2 plus 3, it's stupid, the screen doesn't go as far. But we were traveling at 8 meters per second. We accelerated at 2 meters per second squared for 3 seconds. So this means we must have went up by 6 meters per second. 6 plus 8 is 14. So we ended part 2 traveling at 14 meters per second. Well, your ending velocity of part 2 is your beginning velocity of part 3, and that's where this comes into play. We're traveling 14 meters per second. We're going to have a negative acceleration, which in this case is going to be slowing us down, and then that will take us 2 seconds to slow down. So now we know that the time associated with the third part is only 2 seconds. So then we go to the position equation. Okay, so starting the third part, we have an initial position of 65. That's where we ended up. We had an initial velocity of 14. That's how fast we got to. And we're going to slow down, and it's going to take 2 seconds. So the minus for a negative acceleration, the acceleration rate is 7, and we're going to do it for 2 seconds. So if you plug that into the position equation, you're going to get 79 meters, which means after this entire story, we ended up to the right, 79 meters, and we are now stopped. Okay. Whew. Question. It says, find the average velocity over the entire trip. Reminder, go to the definition of velocity. Average velocity is delta x over delta t. In this case, the distance traveled and the displacement are the same thing because we never changed direction. And so we went a total displacement of 79. It took us a total time of 9 seconds. 79 over 9 is around 8.78 meters per second. That's on average what we are doing during the entire trip. Okay, so these bigger questions, break them down into their pieces. And in this case, we use the position equation a couple times, and we use the velocity equation a couple times. In this case, we knew we were accelerating and speeding up. We needed to find the new velocity of 14. And on the third part, we were slowing down from 14 to 0, and we had to figure out the time it would take. And the last one is really easy. Just remember, the big 3 equations only constant acceleration. So any time in the future, and we use the big 3, you can only use that when the acceleration is constant. Now, you can use them when the acceleration is 0, which is fine. It's just a super easy question. But any constant. If the acceleration is non-constant, we need calculus. Okay? Calculus is required for any of those non-constant rate problems. And there'll be a couple. And again, we're going to do a whole worksheet where we look at that. But lots and lots of questions in physics and the world have constant accelerations, and so the big 3 are really nice.